And as always, I'll offer to take questions. Either you can raise questions, but you can also raise them via the chat. I will watch the chat, and if I see a question, I'll break it in at the point where it's appropriate in the talk. And of course, there'll be time for questions after the talk. So with that, Florent, please begin.
Thank you. Thank you. It's a pleasure. I assume everyone is hearing me well. Great. All right. I will try to provide some distraction during these stressing times. And also, I must say how much I miss, being in person to seminars and hanging out with people. But hopefully, these times will come back soon enough. Okay, so I want to discuss essentially the approach of solving exactable model for machine learning with statistical physics tools. But the statistical physics is just an excuse to derive a result here. And I will try to really discuss this idea of having a solvable model. All right, so let me start. Okay, so just to fix the idea and notation, I want to discuss problem with supervised learning. Okay, so unless you live in a cave these days, that should be familiar to everyone, but it's always good to fix notation. So this is what I will do. We have some vectors, they're in d dimension, they're called x, and we have some label, y, and we have n of these, okay? And the goal is to try to find a label for each of these vectors. And we have a training set, and the way machine learning works these days using this thing called empirical risk minimization, you have this risk that you average over all your training set, and here you have your loss function that takes the label and a function that you will use. Okay, so the loss can be anything. Popular choices include the square loss, the logistic loss, or square entropy. And of course, here you can use a sample function, like just a linear function. That would be the simplest case. But of course, these days, that will be more complicated function, like a neural network. So, you take your vector, you multiply it by a matrix, a nonlinearity, a matrix, nonlinearity, and so on and so forth. Okay, and in that case, the set of parameters is much larger. So that's what everybody is doing. Okay. And if you open a book on machine learning, you will be taught essentially the kind of following statement. You will be told that the reason why this works is because the error you do when you train is very close to the error you get with new sample, at least if you have some conditions. That's the statement. Okay, the generalization error, so the error you will make when you observe unseen sample, minus the training error, the one you actually minimize, it's bounded by a quantity called the Rademacher complexity plus a term here. And with working hard, you can also try to show the following result, but the Rademacher complexity is bounded by another quantity called the VC dimension. Okay, and the VC dimension is essentially something which is square root of a constant, so that makes the Rademacher complexity bounded by a quantity that goes away when the number of sample is growing. Now, that's beautiful, and there is a lot of work in this direction, and I don't want to trash any of these results. This is great. But the truth is that in practice, we see that kind of approach, which is a uniform convergence on the worst case, so it's really conservative, it's usually far off. It doesn't describe what's going on in reality. And in fact, in reality, we observe often that we have amazingly nice results, even though we are not in the regime where these results apply. So that kind of approach is not the one I'm looking myself, and instead I will try to show you the way I was taught how to attack these questions with this statistical physics mindset, if you want. All right. So what are the things we really want to know? This is a snapshot, snap capture of a paper where they say that these are three interesting, important open questions. Why don't over-parameterized neural network overfit the data? What is a number of parameters actually in practice? And why, when we do gradient descent, we don't get stuck in a poor local minima? So interestingly, these questions are not new. They were asked in a beautiful paper by Leo Breman in '95, and this is the capture of his paper, in a paper called Reflection After Referring Paper for NIPS, which is called NUMERICS now. And it's very interesting that this is still what we are working on now. So there's still much work to do. All right, so as we said, I was trained as a physicist, even though I'm hanging out more with mathematicians, probabilists, and computer scientists these days. And as physicists, you never want, you're not trained into thinking into worst case analysis. You don't want to think into uniform bounds and make no assumption about the data. Instead, the way we are born and bred is by telling us that it's nice to think about models, okay? So it has some downsides, but that's the way we think, and we like to make abstractions and simplification of reality. We like to think of everything as harmonic oscillators, and if we want to think of an animal, we think of a spherical cow in a vacuum. So we do the same with machine learning, and one of the things that it at the core of everyone is doing it these days, but it was really something that was at the core in the physics community, is this thing called teacher-student framework. And again, I will discuss it. But essentially, it's a way to generate some data from a model, and then you ask yourself how much you can do on this model. You try to be as realistic as possible, but usually you are making huge simplification. All right, once you do this, then it's pretty obvious how to do statistical mechanics. Since you have, you're minimizing a function, well, you might as well write a Boltzmann measure. And of course, if the temperature or inverse temperature beta is large enough, then essentially your Boltzmann measure concentrates on the minimum. And so you have turned a minimization problem into a statistical physics problem. And this is really stupid tricks, just taking the exponential of the function. But then at least, we are in a known map, and we know to work with the problem. And typically the kind of thing that you have to do as a physicist here is to compute the average of this log of the normalization here called the partition sum. And physicists like to do this because we have been doing this all over the place. And of course, physicists like to do this, of course. Field theory is also doing this. So we are in a known place. So that's what we have been doing. And as I was said in the introduction, there is quite a literature on this approach. I mean, it goes back to maybe 35, 40 years ago. And just giving you some literature, if you want to read more about the origin of these approaches, that's the classical book, Spengler's Theory and Beyond from '85. If you want to learn more about the mathematical side of these techniques, well, that's much more recent because, of course, mathematics takes more time. So this is the classical book by Talagrand. And there is a very nice review on the state of this idea of statistical mechanics of machine learning as it was, let's say, in 2000. And this is well summarized in this book. Of course, this is before the deep learning revolution. So things are moving fast these days. Okay, so that was a kind of general introduction. These days in my group, we're looking many different problems related to these questions. We try to look at the energy landscape. We are trying to study alternative to backpropagation, which is a standard technique to compute the gradient. We are trying to understand the dynamics of learning in neural network, trying to understand when you should use kernel or neural net. I'm also working with, in trying to prove rigorously some of the prediction from the statistical physics approach. And I also try to understand this thing called the bias variance trade-off. So today I will, of course, not cover all that. And instead, I will try to talk to you about two different sets of works, which are slightly disconnected. And one is about the study of the energy landscape, and the other one is about this thing called the bias variance trade-off.
Yeah, control.
All right. So, enough talking. I will start. Sorry, I'm French. I need my Chardonnay. Okay, let's start. So the first set of work I want to discuss is this idea of learning with random feature neural network. Okay, a bit of motivation. Again, when we are taught machine learning, this is the kind of thing that we are told. If you try to fit with a complex function, well, you will probably fit noise, and it's really very bad. It's called overfitting. If your function is too simple, well, you will not fit the data at all, so it's bad. So you try to be here in the balance case, balancing the bias and the variance. Now, the truth is, in practice, that's not what happens with neural network. When you take more and more complex neural network, there have been a series of work in the last few years, but in fact, if you dig a bit, you could trace back some of these ideas in the early 90s. But what people showed is that, even if you take neural network with more and more and more and more and more parameter, you don't seem to have this bias variance trade-off where things go bad. And in fact, it's often it works way better. And a typical kind of shape that you see is a thing where it goes better, then it seems that you have a bias variance trade-off, so it goes worse, and then suddenly, boom, it gets better again. And this is from a paper from my colleague in EPFL, but it has been seen all over the place. That's a more recent paper with actually much more involved neural net, that's a ResNet. And these days, that kind of behavior where it gets better than worst, and the worst is exactly when the train error goes to 0, is referred to as a double descent from a classical paper from Misha Belke. All right, so what I want to tell you about is a set of work, 2 works actually, where we try to understand this in a solvable model in the spirit of what we do in statistical physics. And it's a work that has been done with 2 postdocs, Federica Gerace, Bruno Lorero, with Marc Mézard, who is one of the pioneers of the statistical physics approach to this problem, and my close collaborator, LANGEVIN. All right, what is the problem that we are studying? Okay, so we are discussing random feature neural net. So it's a 2-layer network in which the first layer is fixed. So we take a random matrix F and we never learn it, and we learn only the second layer. Okay, these are not simply academic problems. These are actually things which are used in practice. There is a deep connection with kernel that was discussed in this classical paper by Ali Rami and Benjamin Recht. In fact, this paper got the Test of Time Award presentation a few years ago in NUMERICAL. And by the way, the presentation by Ali is fantastic, hilarious and entertaining and informative, so I recommend it. And one of the reasons we like this model is because also there are deep connection with what are called neural network in the lazy regime, which I don't want to discuss, but it's worth mentioning that this is really, really an interesting model for this reason. Okay, so what have we done? So first, we have a model of data, and we choose the stupidest model ever. Okay, we have n vector in d dimension, and they are drawn from the simplest function ever, Gaussian, with diagonal covariance. Now for the labels, we choose this function, just any function applied to x times a vector chosen randomly. Okay, so that was actually a model that was set up by Andrea Montanari and Song Mei in Berkeley. And then we have the architecture, and we decided to look at the problem with an arbitrary cost function. So L2 regularization and a loss that can be logistic, hinge, square, pretty much anything convex. Okay, and the question we ask is, can we derive what is the training error and the generalization error? And then in the spirit of statistical physics, we sum quantity to infinity. And here D, the dimension, P, which is the dimension of the intermediate layer, and N are all going to infinity with fixed ratio. Okay, so it's a similar of thermodynamic limit in physics. Okay, so what is it? Well, 10 pages of computation later, this is the solution. So if you consider the unique fixed point of this admittedly ugly system of equations, but not a complicated one, then I claim that in the high-dimensional limit, the generalization error is given by this average over two random variables, which are simply two-dimensional Gaussian, so it's a two-dimensional integral. The error, training error is just given by the scalar, and so we have answered the question. Okay, so if you look at this formula, which I will not derive, have been derived with heuristic statistical physics method, namely the replica method. You recognize here the loss. This function is actually the proximal operator of the loss. Here you will recognize in this calligraphic zeta that there is the function that is giving the true label. G that happens here and here and here is actually the still just transform of FF transpose. FFF is simply the matrix which is in the first layer of my model, my network. And you have this constant here, which are connected to the kind of activation that you are doing. Now, for some of you, that might look familiar, and it should, because one case was actually solved rigorously recently, and this is the case where you are using the L2 loss. In the L2 loss case, all this problem can be mapped to a random matrix theory problem, and then you can apply straightforward random matrix theory, and you can solve it. And that was done beautifully. And it was discussed in this set of work, but it's especially in this amazing paper by Songmei Andrea Montanari that was serving as an inspiration. So of course, this is much more generic because we have any sets of weights. And the weights don't need to be Gaussian. FF transpose can be arbitrary. We have the Stieltjes transform here. And what is more interesting, perhaps, is that we have any loss. And you will see that the choice of loss is making a difference. So we have this equation for a while, and recently, my colleague, Yue Lu, who is actually in Harvard, and I can see here in the audience, hi Yue, just told me that he managed to repeat the whole computation rigorously using Gordon minimax and other tricks. Actually, it's I don't want to go into the detail. There are a lot of very interesting phenomena behind here, including some universality. And there is beautiful math here. But anyway, so now we know that these things are correct. So that's great. All right, let's look at what the solution is telling us. So we pick up a classification cask. And here what I show you is what happens when P over N is increased. So N is the number of training example, and P is the size of my intermediate layer, okay? And it's also my number of parameters. So I'm increasing number of parameters, and this is what I get. So if I have the square loss, well, I have this double descent, it's diverging at 1, and then it goes back again to a good value. And that's exactly what was shown first by May and Montanari. Interestingly, you see that the behavior with the logistic loss is a bit different. While you still have a peak, you can still reproduce the same phenomenon, but the transition is elsewhere, right? And of course, if you try to use regularization and you don't use lambda close to 0, then you can kill that kind of effect, and you have a beautiful curve, which is much better, which is what I'm showing you here. All right, and of course, the peak corresponds to the moment where the training loss goes to 0, that's for logistic, and this is for the square. Okay, so what is going on here? Well, I'm increasing the number of parameters so I can fit better and better. So for instance, if you think about the space of zero energy solution, okay, well, there are no energy zero energy solution when P is smaller than N, then there is one, and then it grows and it's a convex set. Okay, and grows and grows. It's the same for logistic loss, but since logistic is a bit clever, it actually tries to find really the best separability transition. It has a transition a bit before, I mean, quite before, but the phenomenon is the same. Now, of course, we need to remember that here, even when I send lambda to 0, I'm picking up one of these solutions. Okay, there are many solutions, and it's not that I find a random one. I find one that is selected by what I'm doing. And this is really important. It's actually not a any solution is one with particular properties. In fact, we know that if you take lambda very, very small, well, logistic converges to the max margin. That is a solution which try to push more on the left and on the right, all the things that it separates. While L2, if you do L2 lot, it converts to the least norm. So of course there is some regularization. And this is, once you say this, then there is no more mystery why there is any of these bias variance trade-off. There is no mystery. You are regularizing, so there is no paradox. Still, it's interesting to continue. And another thing you can show is that even if you don't regularize at all, and if you start from small weights in the second layer, you can also show that logistic and L2 convert to the least norm at the max margin. So that kind of picture is really what you see. Okay, fine. So we can reproduce this double descent, and we are happy. Few things that are worth noting, which I think are interesting. You can, well, first of all, even though the computation is done at, in the asymptotic regime, it works perfectly when, D is 100 or 200. So here you have a comparison with numerics, and you can see it's perfect. And there are some interesting effects that you can study. For instance, you can try to see what happens if you use a random Gaussian matrix in the first layer or a Fourier matrix, a random subsample Fourier matrix, an orthogonal random matrix. And interestingly, you can see that orthogonal random projection always gives better generalization. And that's interesting because it's something that has been observed many, many times empirically in practice for these systems. So it's nice to see it again. So here now I'm showing you the full phase diagram if you want. So you have the three things, N, D, P, and the generalization. So of course, when P is increasing, it gets better. When the number of data is increasing, it gets better. And you have this peak here, this double descent peak. And you can see this line now on this diagram. And this line, of course, corresponds to the moment where you can actually feed the data with logistic without error. And it's exactly the analog of a phase transition that was discussed recently. Well, it was first discussed quite a while ago by Cover in '68. But there was a beautiful paper by Pragya and Emmanuel like 2 years ago. We discussed exactly that kind of phenomenon where you go from non-separable to separable transition for some model of data. And we have the exact analog here. And we can even make a phase diagram. And the line where you go from non-separable to separable data, or if you want to a point where the logistic estimator exists and when it doesn't exist, it depends on the kind of matrix you use. And it's really neat that we can compute out. All right. So this is nice. And now this model is, okay, show us that we can reproduce this in a solvable model. We see that overparameterization does not hurt. And you might ask why. And it's always nice to try to get hand-waving explanation or why is it so. Now we just reproduce the phenomenon, but I would like really to understand and have an intuition why is it so. So that was the subject of a subsequent work that was published in ICML. Actually, the two papers were published at the same conf. And that was a paper that was done with Stefan Dascoli, who's at Facebook, Maria Raffinetti, who is a PhD student with me, my colleague Giulio Biroli in École Normale. And it's called Double Trouble in Double Descent. And what we try to do is, well, just to deal with this problem once again. So let's specialize to the case of the square loss. And the reason we did this is because we wanted to use random matrix theory. So we came back to the specific case that was considered fair by Andrea and Song. And what we try to think is, okay, let's try to see where is the error coming from. Now we know error is coming from bias plus variance. So instead of plotting the generalization error, it may be interesting if I'm plotting the variance and the bias. So we need to define this thing. The bias is essentially the unavoidable error, okay? So that's the true label. And that is what I get with my estimator. And now if I'm average the estimator on any kind of additional noise, any ensemble of data, and any possible random projection, well, that tells me the bias. But there is a variance. And actually, you can decompose the variance into many different components. You can single out the variance due to the fact that you start to overfit the noise that you may have put into your labels. There is a variance term and an error that is coming from the fact that you have a finite training set. And in the variance term, that is coming from the fact that I had a particular choice for my first layers. Okay? So we try to compute all those terms, and it turns out that this is simply a random matrix theory problem. So these are the matrix that you have to consider. You have to compute all these traces. We didn't try to do it rigorously, actually. That was all done with replica in this case, but it works perfectly. That's a nice open problem to prove this result. I don't think this is very hard. Probably a bit tedious, but not very hard. And you can see that all these quantities, psi1, psi2, I mean, these are annoying traces. We can estimate them perfectly with our theory, which is given by the lines, and it compares very well with the points, which are simulations, okay? All right, so what have we seen? So this is what we have seen. When you increase the complexity, what happens to the bias? The bias is given by the red curve. And of course, the better your function, the more parameter you have, the better it is able to fit your data, so the bias should decrease. And it does. But what is interesting is that it has a phase transition, it decreases and boom, it stays constant exactly at the interpolation peak when you have zero error. Which perhaps is not so surprising, I mean, you have a vector that you try to feed with p parameter, and as long as you have p parameter, then you have enough power to fit the function. So this is what's going on with the bias. Now, our three variances, this is what they do. One of them is this one. That was a sampling variance. So this is the one that is due to the fact that we don't have an infinite sample. So it grows. So we have a bit of overfitting. And again, stay constant. So, okay, not very exciting. These other two are more exciting. So the black curve, by the way, is the sum of everything. So the green and blue are the one due to the fact that you fit noise, that's the green, or that you have a particular choice of random features. And it's not an infinite number of random features. And this one is the blue. It's called initialization variance. I'm just saying this for experts, because if you are going into the lazy regime with NTK, it's really the way you initialize your neural network. So if you want to think of this as a theory for lazy regime, go ahead. All right, so the bias decays and I phase transition, but the variances, they diverge at the peak, and they are really the one that annoy you. And they diverge and they decay again, okay? And so the reason why you don't have overfitting is really because of the decay of these two variances. And so if you try to look at what is going on, well, it's some kind of self-averaging, to speak like a physicist. Overparameterization helps because when you have a too big system, what seems to be going on is that the large system is becoming basically behaving like a collection of small systems. And it's, averaging because, you have a dependent system and the variance is divided by the number of effective independent systems, right? So that was an idea that, I heard first by my colleague in EPFL, and I was kind of dubious, and this is why I did this work. And it seems to be quite solid, actually, in this regime. And what it means is essentially, in practice, your neural network that looks like this, it's behaving like this. Like, you're doing some random projection some random projection, and it's almost like if they are independent. And then you average them. So it almost looks like it's averaging a dependent system. And if you take that kind of analogy, literally, you might want to say, haha, but maybe this is an interesting thing to do different random features and then average at the end the prediction. And it works very well, and you will see it. So again, I want to come back to a point of history. So you see you have these variance that increase and goes back and back down, and the bias is doing this behavior. Now, as I said, when you looked at the literature, the classical paper that everyone was citing, saying that there is a bias variance problem with neural network, was this paper by Gaiman, Bienenstock, and Dorsat in '92. But when you read the paper, they say exactly the opposite. They said that they were surprised because when they were trying to understand bias variance trade-off in things like nearest neighbors, they actually see the bias variance trade-off. But when they were looking at it for a problem like neural network, they could not see it. And they said, oh, it's probably something we should look at. And somehow that was forgotten. But if you look at what they see, they say, okay, the total error is decay. And the bias is doing something even as a plateau, while the variance is growing and then decaying again. So it's kind of cute that we reproduce this. And, I mean, we should cite back again this paper, not that he needs it, of course, but it's interesting. Now, as I said, the last thing that we did was to say, fine, if this is, if this is something interesting that you are trying to learn a neural network and with many features, and it behaves like independent neural network, each of them with its own features, and it's then average, well, you might do directly the second one, because it's easier computationally to train with smaller networks and average them. And so we also computed the error that you get if you do this. This is called ensembling. And again, this can be done from the matrix theory, and it's part of the paper. All right. So that was the first thing I wanted to tell you. And I think this is interesting. It's one example where that kind of approach, when you solve exact models, can hope, I think, give insight to what is going on to this problem. Okay, I think I'm doing well on time, so I will attempt the second problem, if you don't mind. It's Swiss wine, actually. It's not so bad, but not as good as French. Sorry, it's 9:30 here in Europe. All right, so let's move to something slightly different. I will discuss now a model to understand landscape in this problem. So again, it's a collection of work, a series of work published recently, ICML, NeurIPS, and in Physical Review Weeks. Were done with postdocs, well, one postdoc actually, Stefano Serrao, and my colleague, Professor Giulio Biroli, Lenka Zdeborova, Chiara Karamota, who is actually now, she left King's College, I think she's back to Rome, and Pier Francesco Urban. All right, so let's come back to this problem of learning in complicated landscape. So one of the questions that we'll all have, and in fact, even the people who invented deep learning had at the time, Yann Lequin told me once that Hinton did not want to do gradient descent because he thought it would never work. So, Hinton is, why does it work so well? Because, our intuition is telling us that we should have very complicated landscape and it should not work. Especially because the gradient, it's quite a stupid algorithm in many ways. It's pretty like being blind. You go down, and if you try this in Switzerland, I think it will be a bad idea for you. I don't think you will end up in a nice place. You'll probably drone here or get stuck in a tree. Yet it works, and so one of the questions we may ask is why. Okay, and what is the interaction between the energy landscape and the gradient descent algorithm? And why are we not bothered by these spurious minima? Or maybe we are, and why are sometimes we are and sometimes we are not? So a typical answer that was pushed in over over the last few years, and has gave rise to an amazing amount of beautiful work. So I'm not citing everyone here. I'm sure I'm missing many people, but it's impossible to be exhaustive here. Is essentially to show that in many problems, you can actually show that if you have enough data, you don't have bad minima. And you can show this all over the place. Okay. Now, the trouble with these approaches is that if you actually put numbers on them, and it's something sometimes people in computer science or rigorous work don't do, they say, oh, it exists n such that. And then you ask, what is n? And say, I don't know. And try to think what it could be, and you realize it's larger than the number of atoms of the universe, so maybe it's not very relevant. Okay, and so you think, okay, what happens in practice? And you realize that in practice, you have gradient descent that often work just fine in a regime which is not at all described in this paper. Okay, so it's worth thinking that maybe something else is going on. It's not just that everything is convexified. That's a bit too naive, at least in some regime. Okay, so what do we need? Again, what we like, statistical physics mindset, we want an analyzable case where we can do everything. So we need to be able to compute optimal performances to know what is the best thing we hope. We need to be able to compute what is the behavior of gradient descent, because that's what we want to analyze. And we also need to compute the properties of the energy landscape, because that's what we want to compare with. So it's not easy to have this free ingredient, but this can be done in a very simple model, which I really like, which is called the spiked matrix tensor model. So of course, it's way another league. It's not the same league as neural network, but at least I can do all these things. Okay, so it's not entirely out of the blue. People love matrix and tensor in machine learning. You are using all over the place this thing to work. PCA in kernel PCA is just matrix factorization. So it's really about factorizing a matrix in low rank 1. Actually, you can do a lot of things with tensor PCA. That's a nice paper that I like from my colleague Surya Ganguly over in Stanford. And there are a series of work by Anima Anand-Kumar, who is the champion of using tensor in machine learning. So go watch our talks. Yeah. So here is what we do. We look at a very simplified version of this problem. Here is the problem. We start by generating a random hidden vector, x star. And I'm not giving you this vector, I'm giving you x star and x. I'm giving you a matrix xyj, which is xi star, xj star plus a random noise. And I'm giving you a tensor, which is ti1, i2, i3 is xi1, xi2, xi3 star plus noise with some kind of clever rescaling to make the problem interesting. And of course, I could have written the problem this way. It's really the rank 1 version. So this is the rank 1 matrix plus some noise. And this is a rank 1 order P tensor plus a noisy tensor. And now your problem is given this tensor and this matrix to try to guess what x star was. And this is a generalization of a problem called the Spike-Wigner model in statistics, and that has been also studied all over the place, especially by David Nono and Johnson, Gerard Benarous, and others. All right, what do we know? Well, we know quite a lot. First of all, we know what is the best error you can ever get on the construction. And this is the result. It's actually something that we first derived with the replica method, and then we proved with a technique called interpolation techniques. And the result is that the best error you can get is 1 minus m star, where m star is the maximizer of this function. Okay, quite neat. And what it actually means is this. So this here is the amount of noise. Delta 3 is the one I'm adding on the tensor. Delta 2 is the amount of noise I'm adding on the matrix. And this is the best, the minimal error I can get. So you see that there is a region where the minimal error is 1, which is the same as a random guess. So that means that in this region, you cannot beat a random guess. And then with a phase transition, when you can get something much better. And of course, if you send the noise to 0 in both directions, then you can go to a perfect reconstruction. Okay, and it's nicer to look at this in log-log. Okay, so that is optimal learning performance, but we don't know how to do this in practice, because optimal learning performance, you can do it only by Bayesian analysis, and it means being able to integrate function in high dimension, and we don't know how to do this efficiently. So the question is, oh yeah, sorry, I'm going ahead of myself. So instead of looking to this diagram, I will look it by above. Okay, so here we have the SNR, 1 over the noise of the matrix. Here you have the noise of the tensor, and this is what we have. You have the region where the best reconstruction is error, which is 1, or m star equals 0 if you want, and here inference is possible. Okay, so it's clearer to look at this than looking at this fancy 3-dimensional. All right, so what we want to know now is what you actually observe with an algorithm, and by an algorithm I mean gradient descent. Again, gradient descent here, well, we just write maximum likelihood. So we say, fine, I want to minimize, well, the difference between the observed tensors and the rank 1 tensor xc star, the observed matrix and the rank 1 matrix xc star, plus the observed tensor minus the x, tensorized, sorry, it's getting late, x to the tensor of order p, right? The one you construct. So you minimize x and you want to minimize this function over x. That's your maximum likelihood. If you're a physicist, you recognize that this is the energy function of a problem called the p-spin model, which is really the one that physicists working on this other system have been working forever. And it was introduced by Gross and Mézard in '84. And this is really the bread and butter of physicists. So this is why we choose this model, because we knew, we just had to go in the literature and we will find the solution, which we did. All right, so how do you study gradient descent? Well, we know how to do things. There are literally hundreds of papers telling how to do gradient descent with a noise, which is what physicists call the Langevin algorithm. And the way you obtain gradient descent, or in that case, gradient flow, is just by sending the noise to 0. Okay, so there is this mapping from Langevin to gradient. And so what we had to do was just to follow the literature on this model. We took back what was written about how to analyze the Langevin equation, send the limit of temperature to 0, and voila. So these are the classical papers on the Langevin equation for this problem. They are due, well, to Pugliangolo and Kurchan, Crescenti, Horner, and Sommers, and there is even a rigorous proof, which is due to this beautiful work by Gérard Benarou, Samir Dambo, and Alice Guionnet. So we know exactly what gradient descent is doing. It follows a set of PDEs, which I'm just writing here. It's not very, very informative, but this is what is going on. You can really analyze gradient descent by just solving these PDEs over these functions. These are called correlations, the response. The only difference with the published work that we had to derive, because of course everything was not done for this, it was done for a slightly different model. So we had to work a bit. So this is what we had to do. So we had to work, and that's a new thing that we had to have the C star, but no matter. So these are equations that then we can analyze. So we work hard, we derive them, when we analyze these PDEs, and we try to look at what they tell us about the behavior of gradient descent or gradient flow at long time. And this is what we found. From numerical simulation, we found that if you run this equation, there is a region here where gradient works, and it finds a correlation solution correlated with X star at long time. And there is a region, that is everything below this line, where it does not work, and gradient is stuck in spurious minima, which have no correlation whatsoever with the truth. And if you work hard enough, you can also derive the formula of the line that separates these two different regions. Good, so now we know exactly what gradient is doing. Fine, but what we really want to know is how much it's connected with the behavior of the landscape. So we have to study the landscape. All right, so let's study the landscape. So that's an energy function. And what we try to do is to say, fine, how many minima are there? Are they bad? Are they correlated with the truth, or are they not correlated with the truth? Again, all these questions, can we still compute the property of the energy landscape? Can we compute the number of minima in Sano? These are things that have been considered in the literature of spin glasses quite a lot. And in fact, for this problem, even very recently in mathematics. So again, it was not too hard. There are a set of works that tell us how to do it. Essentially, this thing called the Katzreis formula that was introduced in this context by Oeffinger, Benarus, and Czerny. And okay, I will skip it. I don't want to go into detail, but essentially, it's a way to compute the logarithm of the number of minima and saddles.
Question from Eric.
Yes.
Eric, would you like to ask or?
Sure. It's just asking whether this analysis of actual gradient descent, I think, can be extended to analysis of stochastic gradient descent, which introduces batches for computational costs.
Yeah, very good questions. Yeah, we are trying to do this. So we have a set of work when we do batch and mini batch, but this is for a much simpler problem. It's really for a perception. But in principle, yes. So of course you need to make a field theory, which is a bit more complicated, but yes, it can be done. And so it should be done. That's clearly, it's actually, you know, in next few slides, I will say to do stochastic gradient descent. Okay, but now I'm moving to landscape, so we have a Katzreis formula that allows us to study this. Again, we are in luck because Gérard Benarus, Sonmei, Montanari, and Nika looked at a very similar problem recently, which is exactly this one, but only with the tensor. So in our case, we observe a tensor and a matrix. So we just had to repeat their computation, and you know, it's not so hard. It's just change a bit the formula, and so we have this, you know, these numbers that tell us exactly how many minima they are, with which overlap with the hidden assignment, and what is the energy with respect to the matrix and the energy with respect to the tensor. So we know everything. Okay, so what do we find? And again, instead of showing formula, I will show you cartoon. It's less precise, but usually more informative. So this is what is going on. If you have a low SNR, or if you have a large noise on your observed matrix, on your observed tensors, the kind of thing that you see is this. At large energy, you have many saddles. So you know, this thing slow down your dynamics, but eventually it cannot stop it. And if you do a gradient descent, well, it will go slow and slower, and it will stop somewhere when it meets minima. And you can compute the number of minima, and there are exponentially many minima starting at a given energy, which is called the threshold energy. And there are a bit less before, and so on and so forth. And the minima that you really want to find are here. So you think that your dynamics will get trapped here, and will never find these good minima, which I plot in blue, which are much lower. Now, when you decrease the noise, or if you prefer, if you increase the signal to ratio, you have that kind of behavior. You are killing these minima. Cool. And at some point, you kill all of them. And there is only one minima which is left, and this minima is correlated with the hidden assignment. So we call this a trivialization line, and you see this is exactly the kind of idea that I was discussing before. There is a moment where you have, you know, trivialized your landscape. Good, so problem solved. Let's try to see in this phase diagram where this trivialization takes place. Trouble is, it takes place here. So here everything is trivial, so dynamics is working, but here it's not trivial. We still have exponentially many spurious minima. They should trap our dynamics, and they don't. Because I remind you that this is, that was the line that we observed with the PDES. So there is a small phase here with exponentially many minima, and yet it works. So why? So if you want to understand why it works, and I think it's really instructive, we have to come back to the landscape analysis, and we have to wonder what happens to these minima when we increase the SNR. So if you pardon me the stupid joke, you have to care of the fate of the spurious minima. I'm sorry, I could not resist. And that's really the key, you know, the fate of the spurious minima. What happened to them? They just don't vanish like this. What happened is that these minima here, when you increase the SNR, they actually become saddles. There is one direction that open, and this direction is going into the direction of the spike. Or if you want, what is actually going on is that if you look at the spectrum of the Hessian, it has a BBP transition for those who know this work, and with one eigenvalue that goes out, and it's pointing really, really in the direction of the hidden assignment. And you can actually see this from the random matrix analysis and the cat-right analysis. So instead of this line, we may try to compute the moment where the first trapping minima start to have this negative direction. And the idea is that once this happens, well, your dynamics is easy because you go there, but it's kind of get trapped. You are sent into another direction and you go straight away toward the good minima. So is it true? And the answer is yes, because if we compute, if we plot the line where this is going on, this is the same line. So this is what is really happening in this model. It's not that suddenly you don't have any minima and everything is trivial. It's that suddenly the landscape is conspiring, there is conspiration of the high energy minima and they start to have good direction and you don't see the spurious minima, even though they are there. So I think that was a very interesting example of what could happen and how you could get some insight from the idea of landscape. And yes, we have a lot of open problems. We are trying to understand what's going on in perhaps more relevant problems, including things like phase retrieval and so on and so forth. And ideally, we would like to be able to repeat that kind of analysis in neural networks, study the role of characterization and other gradient-based algorithms such as SGD, maybe including Nesterov, momentum, and so on and so forth. All right, I think my time is up, so which is good because I'm done. So I showed you some example of exactly solvable model of statistical machine learning that we attack with rigorous and non-rigorous method from statistical mechanics, whatever works. And I hope I convince you that these models shed light on some interesting phenomena in these matters. I want to thank all the people that worked with me on this. And again, a bit of an advertisement. LANDCSAPE and I just moved in Switzerland. I myself created the EDFX lab. We are looking for talented students and postdoc. If you know some, give them my contacts. We are hiring. And with this, I'm really done, and I thank you for your attention.
Thanks, Florent. Very good talk. It's a cute name you have for your lab. Did you think of that, or?
No comments.
Yeah. Are there questions out there?
I'm glad you like it.
Questions?
Florent, I have a question.
Yes.
Thanks a lot for a very interesting talk. Can you go to your slide on the landscape where you have the saddles?
The cartoon.
The cartoon, yes, please.
All right.
So when you have when you have the saddles, then my understanding is you have a high dimensional, n-dimensional Hessian, but there's only one direction that is the correct direction, right?
Yes.
So that means because the dimension is high, the algorithm will take a long while to find that correct direction, right? Is that the case?
So yes, so this is what is going on. So I'm just running the algorithm for you in real time, and you can actually track what is the Hessian at each time.
Sure.
And this is what's going on. So here you have the magnetization, how much you correlate with the hidden assignment with time. And you see that at the beginning, when you look at everyone around you, well, you start half direction are negative, half are positive. And of course, you go down you have less and less negative direction. So the algorithm is getting slower, actually.
Mm-hmm.
And at some point, you have just one negative direction, okay, which is this arrow. And when you have only this one, up, suddenly, boom, your magnetization jump. So the thing is, at some point, you have, you have this phase transition where, if there will not be the planted state, you will be in a minima. And yes, at some point you have something negative to develop. But going there might take some time, and it's not a very efficient algorithm indeed.
But the transition looks on the right looks pretty fast, around 500. But you're saying what?
Yes, yeah, no, but because once you go, no, once you cross and you go into the right direction,
that's very fast.
Yeah, then it's fast. Then it's fast. Then you go into a kind of nice basin, and that's easy. So the hard work, is evolving here. And at the beginning it's easier. You go down, then you have less and less negative direction, and at some point it gets slow, and
I see.
And so on and so forth.
I see. Thank you.
This was for your matrix tensor model. Do you think there's a similar picture for like feed-forward network and supervised learning?
Well, I'm a very optimistic person, and I like to think so. But of course, this is an extremely naive view, and so I would not claim any relevance. But I think it's one realization of a scenario where we can understand what is going on in this picture. So for this, it has some merit.
Oh, is it crazy to think that a neural network landscape has this qualitative behavior?
No, it's not totally crazy, but it's way more complicated, right? There is not one hidden solution somewhere, and there is nothing that is, here everything is pure. Ever I have something bad, ever I find the truth, right? And that kind of notion doesn't exist, at least in neural network. But
well, you have teachers.
Yeah, I mean, I'd like, it's really teacher-student-y, which it's good, but I'd like to think that it has some relevance, yes. But at least I think what it shows is that you don't have to subscribe to the all minimas are good theory. You don't have to. It's one example where no, some of them are bad, but if you don't see them, so I would say it's an example of the scenario. Then who knows?
More questions?
Flora, could I ask something?
Yes.
Thanks so much.
Yes, it's
great talk. Yeah, I was actually just
great to see you.
Yeah, it's great to see you. So I was just wondering, I mean, in the teacher-student kind of scenario, for the Bayes problem, because you usually know that your posterior distribution is replica symmetric, right? If you actually decided to do like Monte Carlo, right, as people in Bayesian statistics do, so you run some Markov chain that has the posterior as its stationary distribution, does the Coglianello-Courchan approach actually predict what will happen in this case, and what should we expect?
Yes, definitely. I mean, we can analyze Langevin dynamics at finite temperature. Then it's not exactly the same as Monte Carlo, but it's close enough. Yes, we can. And for this problem, okay, let me come back here. That's exactly why people develop these techniques in the first place.
Right.
To look at
the unplanted case.
And so that's exactly. So our modification to the literature was really minor. We just looked at the planted version, and so that's what we discuss in this paper. And actually, this first paper here, the Marvel and Pitfalls, which are a grandiloquent name, is really about. It's really more about the behavior of Langevin for Bayesian estimation at finite temperature. Like with matching posteriors and everything.
Sorry, so just to follow up briefly, I mean, in that case, I mean, because, I mean, I'm just wondering, because the entire distribution is kind of replica symmetric, then is it easier actually in that there is no effect of these spurious minima and stuff, or qualitatively I'm wondering what would be different?
You know, it is replica symmetric, but the equilibrium is replica symmetric. So,
so the off,
you know, right? But the off equilibrium
could still be bad. I see.
Right, and you know, that's the problem, and unfortunately, yes, you still have some hard things that are going on to your dynamics.
I see. Thanks so much.
More questions?
Thanks for the talk. Can I just ask something?
Sure. I need to figure out who's talking because
I'll turn on the video. Hi. So if you go back to the picture of the landscape where you have those minima that transform into saddles.
Yes. Like, the fate of the spurious.
Yes, exactly. It looks like the geometry there is still one where you have an exponential number of spurious local minimizers, but just at a lower energy.
Yes.
And is there a reason why you end up at the saddles as opposed to these lower energy minima?
You know, that's the limitation of drawings, I guess. I mean, what we know is to show. I mean, what we know is that if there would not be any signal, and if the the tensor, the matrix will be random, we know that at long time you end up here. So it's not so crazy to think that, okay, as long as as I don't see that there is a signal, everything is like ending up here, and then it makes sense that I should try to understand what those guys are doing. But I don't know how convincing this is. I mean, this is what is going on, but
like, can you count the density of minima?
Yes.
Because you know that you have more saddles than minima.
Yeah, that's definitely what we have done. We counted all those things. And we compared with what is going on with in the dynamics, and we looked. Where are you? Oh, you are really there. So this is really what is going on. And the reason why we are sure is because we really compared, the property of where we are and the Hessian and the dynamics are where we are, the number of landscape. We counted how many. That's literally what we did here.
Okay, thank you.
More questions?
Can I ask one question?
Please.
Hi, Sarah. So I guess my question was, you said like large networks are doing this self-averaging thing. So it's like averages of small networks.
Wait, you're sending me back to part one.
Yeah, but I guess the question was more sort of conceptual, that why are they necessarily ensembling using averaging? I mean, one thing I haven't seen reconciled in the literature is actually ways of ensembling simple things, like boosting, bagging. These are all like very powerful ensemble learning algorithms.
Yes.
So I'm just wondering if people have
much powerful than the one I'm doing, which is a very naive ensembling.
Yeah, so I'm just wondering if people have looked at, if you took simpler networks and ensembled them in a bit more complicated way, then what happens? Like, do you get like large networks with extremely good performance, or like what really happens? I don't have looked at this. So
that's a great question, and yeah, it's on my to-do list. I'd like to look at this. It's I agree, right? And why, if instead of just averaging them, I'm boosting them?
Yeah, why don't you like boost simple, like a bunch of simple networks, and what would happen?
I didn't do it because that was easier to do it this way, and easier to code, and easier to compute. but that's not a good answer. So you're right. I don't know the answer, and maybe it's super good, or maybe it's just the same. But in both cases, it will be super interesting to know. And I don't know. I really don't know.
Okay.
And I'd love to find out.
Okay, great. Thanks. Yeah.
Thanks. Any more questions? If not, let's all thank Florent. We can unmute.
Well, thank you, everyone. And I hope to see some of you eventually, in a not too distant future.
Someday we'll be able to do these things physically. Let's hope.
Yes.
Thank you for a great talk.
Thank you so much, everyone. It's great to connect with my friend overseas.
Thanks.
Bye-bye.
Bye-bye. So next week we will have Eric Milnes from Irvine, who still needs to tell me his title, but we will be there. So see you then.